This is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about engineering tribology. So in this subject, we have discussed in the previous sessions about friction, wear and lubrication. So in this today's session, I want to explain about electrochemical theory of corrosion. So already we have discussed about corrosion. What do you mean by corrosion? And then types of corrosion and how to prevent the corrosion and methods, and then various factors affecting the corrosion we have discussed in the previous session. But in this topic, so we will see electrochemical theory of corrosion, and then other miscellaneous corrosion types we will see after completion of this electrochemical theory of corrosion. You know, the corrosion under this chemical, one is chemical corrosion and another one is electrochemical theory. Two corrosions are there. So in this, this type of corrosion occurs where a conducting liquid is in contact with the metal. So in previous session, we have discussed about chemical corrosion. So whereas in chemical corrosion and then this type of corrosion, so what is the difference between these two means, so in this corrosion occurs in presence of liquid. So without a liquid, in presence of environmental gases, so that corrosion is called as chemical corrosion. So you know, this type of corrosion occurs, so whenever the conducting liquid is in contact with the metal, so the metal surface directly contact with the liquid, so that is electrolyte. You can say water is a liquid electrolyte. This corrosion occurs due to the existence of separate anodic and cathodic pots, between which current flows through the conducting solution. So in this, again, the electrochemical and the chemical reaction between the metal and the liquid happens in chemical corrosion. But in this, it needs some current, electric flow through the conducting solution. In previous also there is contact with the solution. So in case of gases present in the atmosphere, the metal contact with the gases, atmospheric gases, that is dry corrosion. But this electrochemical corrosion comes under wet corrosion. So two types of corrosions are there. So one is dry corrosion, another one is wet corrosion. So in dry corrosion, you know, whenever the metal surface exposed to the atmospheric gases, there is a corrosion, there is a loss of material due to the corrosion, that is the dry corrosion. In case of wet corrosion, again this one chemical corrosion and electrochemical corrosion. In wet corrosion classified into one is chemical, another one is electrochemical. So this chemical, here liquid is required, but they are not required the current flow. But in this, no need of here no need of electric current, here, but here the need of current flow is compulsory. So which current flows through the conducting solution. So at anodic area, oxidation reactions occurs, thereby destroying the anodic metal either by dissolution or formation of components. So compounds, the formation of compounds either by dissolution, destroying the anodic metal, either by dissolution or formation. Hence, corrosion always occurs at anodic parts. So, this type of corrosion is called as electrochemical corrosion. So, the theory, the mechanism behind this electrochemical corrosion, we'll see the mechanism of that corrosion. The electrochemical corrosion involves flow of electrons between anode and cathode. So the anodic reaction involves dissolution of metal liberating free electrons. So the electrochemical corrosion involves flow of electrons between anode and cathode. The electron flows from the anode to the cathode. So in this, some oxidation and then reduction also process happens. So the anodic reaction involves dissolution of metals liberating the free electrons, means here see the metal ion gains electrons, the metallic ions gain and electrons release. So the cathodic reaction consumes electrons with either evolution of hydrogen or absorption of oxygen, which depends on the nature of the corrosive environment. See, in this evolution of hydrogen, this type of corrosion occurs in acidic medium. Example, considering the metal iron ferrous in acid solution, the anodic reaction is the dissolution of iron as ferrous ions with liberation of electrons. Considering the metal ions, so that is diffusion of ferrous into solution of electrolyte and acidic solution electrolyte, and a small cathode is shown in this figure. So in this, the anodic area is large and ferrous anodic area and iron metal. So the evolution of iron, this type of corrosion occurs in acidic medium in presence of acidic solution, that is called as electrolyte. See, in this figure there are hydrogen and then metal ions shown, the diffusion, and then anodic area and the small cathodic area shown. At anode, see the ferrous, the oxidation, the metallic ions reacted with the electrons. So the electrons released flow through the metal from anode to cathode. Here, electrons released. And whereas the H plus hydrogen ions of acidic solution are eliminated as hydrogen gas. So here, the reduction will be happened at cathode. The reduction, the anode oxidation happened. So here, the overall reaction is ferrous plus this 2H plus gives ferrous 2 plus H2. So it means the hydrogen ions of acidic solution are eliminated as hydrogen gas, that is H2. At anode, that is oxidation reaction, oxidation equation, and at cathode reduction equation shown in this slide. This type of corrosion causes displacement of hydrogen ions from the solution by metal ions. All metals above hydrogen in electrochemical series have a tendency to get dissolved in acidic solution with simultaneous evaluation of H2 gas. The anodes are large areas, whereas cathodes are small areas. It's already shown in this the previous diagram. The anodes are large areas, see, and the cathodes are very small areas. The small area is cathode shown, and this is anode area, anodic area. It is very large when compared to this cathodic. So observation of oxygen. For example, rusting of iron in a neutral aqueous solution of electrolytes in presence of atmospheric oxygen. Usually, the surface of iron is coated with a thin film of iron oxide. If the film develops cracks, anodic areas are created on the surface. So why? Because these anodic areas are very large areas. The area is very large. So while the metal parts acts as a cathode, it shows that the anodes are small areas, while the rest metallic part forms large cathode. So the released electrons flow from anode to cathode through iron metal. The released electrons flow from anode to cathode. See, in this diagram, the absorption of oxygen shown, the small anode area produced by cracks in oxide field, cathodic large, and anode area is small. So in this, the produced by cracks in oxide films. Cracks and if the film develop the cracks, anodic areas are created on the surface. So the anode, the oxidation reaction. At cathode, there is a reduction, electron gain, here electron lose. So overall reaction, you can write in terms of ferrous oxide. If oxygen is in excess, ferrous oxide hydroxide is easily oxidized to ferric hydroxide. So you can see, you can write the equation. Ferrous hydroxide is easily oxidized to ferric hydroxide. So 4Fe OH2 plus O2 plus 2H2O. So it gives ferric hydroxide, that is rust. So you can write in terms of 2Fe2 and O3 and 3H2O. So next one is cave-wise corrosion. See, it is a localized form of corrosion that occurs in confined spaces or crevices where the environment differs significantly from the surrounding open surfaces. This type of corrosion is common in metals and alloys, particularly stainless steels, and is often seen in area where two surfaces are in close proximity, such as under gaskets, seals, washers, lap joints, and fasteners. These all are the mechanical joints, mechanical fasteners. Two types of fasteners are, one is permanent type and another one is temporary type. So wherever two surfaces are in close proximity, So in gasket, the close proximity is possible, and oil seals, washers, and lap joint and riveted joints. So these are this type of corrosion is common in this type of joints. So what is the mechanism behind in the curve-wise corrosion? So initial condition, that is, the metal surface is exposed to a corrosive environment. The entire surface may initially corrode uniformly. So oxygen depletion. So in the curve-wise area, oxygen is consumed faster than it can be replenished, leading to oxygen depletion. The change in chemistry. So the difference in oxygen concentration between the inside of the curve-wise and the outside leads to change in the electrochemical potential. So this causes the metal inside the curve-wise to become anodic, more reactive compared to the surrounding area, which becomes cathodic. So the area, the metal inside the curve-wise to become anodic to more reactive. See, the form of corrosion occurs in, this is confined spaces or curve-ways. So where the environment differs significantly from the surrounding and open surface. So that's a change in chemistry. The difference in oxygen concentration between the inside of the curve-wise and the outside leads to a change in the electrochemical potential. Next point is acidification and chloride accumulation. As the metal inside the curve-wise corrodes, metal ions are released, which can hydrolyze and produce acidic conditions. Additionally, chloride ions can become concentrated within the curve-wise, further accelerating the corrosion process. So propagation. So the anodic reaction within the curve-wise leads to more metal dissolution, while the cathodic reaction outside the curve-wise is often oxygen reduction. So this process can cause severe fitting and structural damage over time, even if the bulk material is generally resistant to corrosion. So here curve-wise corrosion shown in this figure, whereas hydroxide and passive film and steel material. So this is the curve-wise corrosion area. So next one is fitting corrosion. It is due to crack on the surface of metal. There is a formation of a local galvanic cell, pinholes, fits and cavities in the metal due to crack on the surface. The fitting is usually the result of the breakdown or cracking of the protective film on a metal at specific points. This gives rise to the formation of small anodic and large cathodic areas. In the corrosive environment, this produces corrosion current. See, in this slide diagram, so the metal is anode is attacked, and the small fit area you can see. So there is a formation of local galvanic cell within the metal. So the fitting is usually the result of the breakdown or cracking of the protective film on a metal at specific points. So generally this type of corrosion environment it produces the corrosion current. See at anode, you see the oxidation reaction equation, and a cathode reduction equation, and overall equation you can write like this. In terms of ferrous hydroxide, if oxygen is in excess, the ferrous hydroxide is easily oxidized to ferric hydroxide. So 4Fe OH2 plus O2 plus 2H2O, it gives 4FeOH3. So the product is called yellow rust, corresponds to ferrous oxide Fe2O3 to 3H2. So at anode, the oxidation happens, at cathode reduction happens, and overall reaction occurred in terms of ferrous hydroxide. Why? Because the oxygen is excess, the ferrous hydroxide is easily oxidized to ferrous hydroxide. The total product is called yellow rust. So that is Fe2O3 to 3H2O. So this is known as differential oxygen concentration corrosion. So it has been observed in the case of iron tank containing water that the portion of iron attack just below the water level undergoes corrosion. It is due to the difference in oxygen concentration. The oxygen concentration at the bottom level and what is the oxygen concentration at above the water level. So the differential concentration of oxygen. So that's why this corrosion is also called differential oxygen concentration corrosion. So in case of this water tank, see the just below the water level the oxygen concentration is different, and the above the water level the oxygen concentration is different. So this is due to the difference in oxygen concentration. So the area above the water line, that is highly oxygenated, acts as cathodic and is not affected by corrosion. However, if the water is relatively free from acidity, little corrosion occurs. This type of corrosion is prevented to a great extent by painting the sides of the chips by anti-fouling paints. So the area above the water line, that is highly oxygenated. So that those areas acts as a cathodic, is not affected by corrosion. So the water is relatively free from acidity. So little corrosion occurs. So generally this type of corrosion we can prevent by applying the painting the sides of the ships by anti-fouling paints. That is waterline corrosion. Here see the waterline corrosion, the poor oxygenated anodic part is corroded, and a highly oxidized cathodic part, that is protected. So due to the differential concentration of oxygen. So the waterline corrosion at anode, reaction given at cathode, the reduction equation, and overall reaction, that is ferrous oxide is easily oxidized to ferric hydroxide. So the product called yellow rust corresponds to Fe2O3 and 3H2. Already I told you in the previous slide. So corrosion control methods are electrochemical protection or cathodic protection. So we have discussed about electrochemical corrosion. So now we are discussing electrochemical protection methods or cathodic protection. This electrochemical protection is also called as cathodic protection. The principle involved in the electrochemical protection or cathodic protection is to force the metal to behave like a cathode. So there are two types of cathodic protection. One is sacrificial anodic protection. Another one is impressed current cathodic protection. Two types of cathodic protections are sacrificial anodic protection. The impressed current cathodic protection also there. See in this, the sacrificial anodic protection. In this method, the metallic structure to be protected to behave like a cathode by connecting it with more active metal, anodic metal. See in this diagram shown the sacrificial anode oxidation and the pipeline which object is to be protected, so all the corrosion will concentrate only on the active metal. So the artificially made anode thus gradually gets corroded, protecting the original metallic structure. Hence, this process is otherwise known as sacrificial anodic protection. So that is aluminum, zinc, magnesium are used as sacrificial anodes. See in this method, the metallic structure to be protected is behave like a cathode. So which one is metallic structure? This one is metallic structure. So this one is to be protected by connecting it with more active metal, that is anode metal. The electrons flows from this anode to cathode. So here at anode, the oxidation happens and at cathode reduction. Here, the artificially made anode thus gradually gets corroded, protecting the original metallic structure. So that's why this method is sacrificial anodic protection. See, you can the important application of this method are protection of underground cables and pipeline from soil corrosion. So pipelines you can see. So this is the before and after rust. The protection underground cables and pipelines. See the ships. Here you can see the ship all protected by using this sacrificial anodic protection method. These are the important application of this method are prevention of rusty water by inserting magnesium sheets or rods into domestic water boilers or tanks. See here domestic boiler, rusty water inserting magnesium sheets or rods. So next one is impressed current cathodic protection. So in this method, an impressed current is applied in the opposite direction of the corrosion current to nullify it and the corroding metal is converted from anode to cathode. The impressed current is applied in the opposite direction of the corrosion. The source of current here shown, anode and cathode, the insulated copper wire and the pipeline acted as a cathode, which object is to be protected from the corrosion. This can be done by connecting negative terminal of the battery to the metallic structure to be protected, and the positive terminal of the battery is connected to the inert anode. Connecting negative terminal of the battery to the metallic structure, the positive terminal of the battery is connected to an inert anode. So inert anodes used for this purpose are graphite platinized titanium. Graphite is shown here. So the anodes used for this purpose are graphite platinized titanium. So impressed current cathodic protection. The impressed current is applied in the opposite direction of the corrosion current to nullify it. So and the corroding metal is converted from anode to cathode. This is done by the connecting negative terminal of the battery to the metallic structure to be protected. Which part to be protected? This is connected to the negative terminal battery is connected. The positive terminal of the battery is connected to the inert anode. So this is anode, the positive terminal connected, here negative. So the anode is buried in a backfill containing mixture of gypsum, coke, grease, sodium sulfate. The backfill provides good electrical contact to anode. So here you can see the pipeline to be protected from the corrosion here. Shown that the anode. So the backfill containing mixture of gypsum, coke, grease and sodium sulfate. The applications are structures like tanks, pipelines, transmission line towers, underground water pipelines, oil lines, ships, etc. can be protected this method. So these are the applications of this impressed current cathodic protection. So in this, we have discussed about sacrificial anodic protection, and then impressed current cathodic protection. We have discussed two methods here. So in this, we have shown this waterline corrosion in waterline corrosion equations, and then corrosion control methods also have studied and shown the important application diagrams. So for this PPT, I have taken references engineering tribology, Stoichiovic and GW Stoichiovic and AW Bachelor, that is Butterworth Heyman Publishers, SK Basu and SN Sengupta and BB Hauja. The title of the book is Fundamentals of Tribology, and then the Mechanical Engineering Tribology website have taken some information. So these are the references I have taken for this PPT. You can refer any textbook for further more information. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.